To find the asymptotes, horizontal, vertical, and oblique, we first analyze each of the individual rational functions. So let's look at this rational function. We have f of x equals the numerator divided by denominator. The first thing we look at is whether it has vertical asymptotes first. So let's first look at the vertical asymptotes. So vertical asymptotes we find by first looking at the denominator. What will make the denominator 0? Well, nothing will ever make this denominator 0 because this is a positive number plus another positive number. You can never get 0. So there are no vertical asymptotes. Now, to either find the horizontal or the oblique asymptotes, we compare the exponents. So if we look at the exponent of the x in the numerator and the exponent of the denominator, you can see that they are equal. Since they are equal, since the exponent of the top equals the exponent of the bottom, that means that we have a horizontal asymptote located at y equals the division of the coefficients. So 9 divided by 3. So we're going to have a horizontal asymptote at y equals 3. So to give you a general idea of what this graph would look like, no vertical asymptotes, but we definitely have a horizontal asymptote at y equals 3. 1, 2, 3. So we'll have a horizontal asymptote there. And if I put this into my graphing calculator, this graph actually would look like this. Okay? So no vertical asymptotes, no oblique asymptotes, just one horizontal asymptote at y equals 3. Let's look at the next one. We have x to the third minus 1 over x plus 2. Okay, vertical asymptotes, we find what makes the denominator 0 when it's in reduced form. So even though this might factor out, it will never reduce with an x plus 2. So regardless if I factored all this out using the difference of cubes formula, I know it will never reduce with an x plus 2, so I'm not going to bother. But I do know that x cannot ever be negative 2. So that means I'm going to have a vertical asymptote at x equals negative 2. So right away I know when x equals negative 2, I'm going to have this vertical asymptote in my graph. Let's also look to see if we have horizontal or oblique asymptotes. We have to check out the exponents. The exponent of the top is 3, and the exponent of the bottom is 1. So we have n is greater than m by more than 1. And by definition from up top, we said if the degree of the numerator is 2 or more bigger than the denominator, there is neither a horizontal nor an oblique asymptote. So this has no horizontal or oblique asymptotes. So this graph over here would actually look like this. Okay. Moving on to part C. Again, looking at the vertical asymptotes first, we would try to factor the bottom and the top, which it already is, and there is nothing that can be canceled. It looks very similar to this first one, except for the degree is a little bit different in the numerator. There are no exclusions from my domain because there's no way to ever get this denominator to be 0. So there are no vertical asymptotes. To find out if it has horizontal or oblique asymptotes, we check out their degrees. the degree of the numerator is 1, the degree of the denominator is 2. So this is a proper rational function where the numerator is less than the denominator. So that means I will have a horizontal asymptote located at y equals 0. Automatically, by definition, if numerator is smaller than denominator, the horizontal asymptote will be at y equals 0. So if I graph this, y equals 0 is actually the x-axis. So since this is my horizontal asymptote, to finish out the graph to give you an idea of what this looks like, now you're going to notice that the graph can pass through a horizontal asymptote as long as it reaches the horizontal asymptotes on the ends, which it does. It gets closer and closer and closer to this horizontal asymptote at the ends, but it actually can make a pass through the horizontal asymptote in the middle near the origin. That is allowed. However, it is not allowed to ever go through a vertical asymptote. Part D, already in reduced form, very similar to the last few examples. Again, the only thing I changed was the degree of the top. So since there are no exclusions from my denominator, there are no vertical asymptotes. Since the numerator is bigger than the denominator, since n is bigger than the denominator by only 1, then I have this option up here which says if the degree of the numerator is more than the denominator by 1, then we find the quotient by doing long division. That will be our oblique asymptote. So this one is a little tricky to do, so feel free to pause the video as you go through this example. So I'm going to do long division. So what we're going to do is we're going to divide this denominator into this numerator. So we're going to divide 3x squared plus 1. We're going to divide that into the numerator, which is 9x to the third. So when we divide that, you're looking to find what term up here, this will be my quotient, my answer is going to be up here. What term, when I multiply it by 3x squared, will bring me to 9x cubed? Well, the answer is 3x. So when we multiply 3x times 3x squared, that's 9x cubed. 3x times, well, there's no middle term. And then 3x times 1. Oops, yeah. So that goes there, sorry. So then I subtract all of this quantity. I subtract all of that. And when I subtract that whole quantity, 9x cubed minus 9x cubed, hey, those cancel out. Nothing minus 3x is a negative 3x. So the next term up here is going to be what times 3x squared will bring me to 3x. Well, since this is smaller than the divisor, there is no second term. We simply just say 0. I really don't care about remainders. Remainders are not necessary to be concerned about. All we really care about is the mx plus b form that this would turn into. So my oblique asymptote is going to be located at y equals 3x plus 0. On a graph, that would be a graph of an oblique asymptote. Going through the y-intercept would be 0 with a slope of 3, which is up 3 over 1. So my oblique asymptote will look like this. And if I graph the rest of this, it's ultimately going to do a picture that will look similar to this. So it gets closer and closer and closer to that purple oblique asymptote, but never crosses it. Okay, let's try one more. I think we need to do another oblique asymptote example. So one more time, we have a rational function, and the numerator degree is again bigger than the denominator degree. So you're going to, oh, this actually was the wrong graph up here. This was the graph of this one down here. This graph up here, which I will now draw, is very similar. Looked like this. So these graphs were backwards. My apologies. Okay, well now we already know what this graph is going to look like. It's going to have an oblique that looks very similar to the last one. Okay? All right, so this graph down here, first thing I'm going to do is I want to find the horizontal or oblique asymptotes. So in order to find the horizontal or oblique asymptotes, what I'm going to do is compare the numerator to the denominator. Certainly the numerator is bigger than the denominator by only 1. Since it's bigger by then only 1, that means we have an oblique asymptote. And to find this oblique asymptote, I'm going to have to divide. So I'm going to take the denominator, and I'm going to divide it into the numerator. Sometimes it's easier to put in placeholders. Since you see that there is some terms missing, I'm going to move the -8 all the way to the end. I'm going to put a 0, x squared, and a 0x inside of there for placeholder so that it's in descending order. Because sometimes that's easier so you don't get messed up like I did on the last example. So when I divide this trinomial into this cubed function, I decide how many x's do I need. So when I multiply by x squared, I get x to the third power. Well, I need 1x. So x times x squared is x to the third, and then multiply them all out. X times -5x, x times 6. Then I subtract that whole quantity. X cubed minus x cubed, those are gone. 0 minus -5x, that's a positive 5x. 0 minus 6 is a minus 6x. And then we bring down the -8. Then we do it one more time. X squared, 5x divides into x squared how many times? In other words, what, that should be an x squared, what times x squared will bring me to 5x squared? Clearly we need a 5. 5 times x squared is 5x squared. 5 times -5x is -25x. 5 times 6 is 30. So you're going to see when I subtract this whole quantity, the first terms will cancel out. That is the goal. And yes, I'm going to have a remainder of 19x minus 38. But nothing else is going to go into that. I don't care about the remainder. All I care about is this quotient, and this will be the oblique asymptote. So y equals x plus 5. So let me redo this graph now that we know the oblique asymptote. So this graph, x plus 5, is going to have an oblique asymptote at 1, 2, 3, 4, 5, and a slope of 1, which looks like this. So this is the slope of the oblique asymptote, and this graph is going to get closer to that oblique asymptote, but then it will branch out and go back down the other direction. So it's only an oblique asymptote in the one direction, not in the other.